Elastic versus inelastic. We can actually classify different types of collisions by whether energy is lost during the collision or energy is conserved. Now, we haven't talked about energy so far, so we'll have to put that idea sort of in the background with this. An elastic collision is one where the two objects collide and then basically bounce off one another, basically with the same energy of motion that they came in. An inelastic collision is one where we have the objects come in and mechanical energy is lost and turned into another type of energy. So elastic we can think of as a bounce-like collision. Inelastic we can think about two things coming together, as in the case of a football player tackling another football player, or an outfielder catching a fly ball. The two objects collide, and then at least some of the energy is lost, or in some cases all the energy is lost, and that's the inelastic versus elastic. But again, we'll come back more to that when we talk about energy. When we talk about kinetic energy. Another important thing that we should talk about when we're talking about momentum is always conserved. When we talk about energy, we'll talk about the conservation of energy law, but just as important is this conservation of momentum law. When two objects come in with some momentum, the momentum of A plus the momentum of B will be equal even after the two have collided. That may seem counterintuitive because sometimes things will come in with momentum and then they'll hit one another and come to rest. Well, in that particular case, the two had momentum, but remember, momentum's a vector. So positive momentum and negative momentum, a positive number and a negative number, if they're equal and opposite, will add up to be equal to 0. So momentum is always conserved in any type of interaction that we have. An interaction is where one object puts a force on another object. This is really a consequence of Newton's third law. You cannot interact with something without it reacting to you. So whatever momentum you give it, it gives you an equal and opposite momentum. Remember, impulse is force times time. Both objects are pushing on one another for the same amount of time. So, a momentum in an isolated system always conserves momentum. If something's in contact with the Earth, sometimes you can transfer some momentum to the Earth. But again, if you think about contact between the two, one object is putting a force on the other. Here's an example. We have two train cars. Both have the same mass, so this is going to make this pretty easy. The first car comes in with 24 meters per second of velocity. That means whatever its mass is, times the 24 will be its momentum. After the two collide, how fast are they going? Well, think about this without even doing the calculation. If both of these have the same mass, okay, and this is coming in with 24 meters per second times the mass of A, when the two are together, when the two train cars have locked together, okay, by the way, if one car is coming into the other at 24 meters per second, that's over 50 miles per hour. They're not going to just, lock up like train cars lock up in the rail yard. They are going to crash. But in any case, let's say that these are super strong cars and they can lock up and continue their motion. Before, this weighed m. This weighed some value m. Now when they're locked together, it's 2m, right? So with twice the mass and still the same amount of momentum, our velocity has to go down by half. Let's see if that's true. We'll do this calculation right here. Here's the momentum before. Let's say that first car A was 10,000 kilograms. 10,000 times 24 is 24,000 kilograms meters per second. And after the two lock up, they still have to have 24,000 kilograms meters per second. I take the momentum, divide it by the mass, it gives me a velocity, and sure enough, after the collision, the second car is only going 12 meters per second. Yeah, it's really simple. We use two identical masses, so the calculations were really quite trivial. But again, if I increase the mass by 3 times, instead of 24,000 kilograms meters per second to be spread over 20,000 kilograms, it'd be spread over 30,000. So from 24, I would have dropped to 8 meters per second. Okay. Here's another example of conservation of momentum. Anytime a firearm is discharged, the force of the bullet, the force that's pushing the bullet forward, creates an equal and opposite force, okay? Equal in magnitude, opposite in direction, pushing the gun backward. The last thing you want to do when you're going target shooting is, if you have a scope, is put that scope right up to your eye. Why? Because before the bullet is discharged, okay, everything has 0 momentum. But afterward, the bullet gets positive momentum, and that gives the rifle negative momentum. Okay? Fastest way to get a black eye by doing that. You want to hold the scope. In fact, the scope sight is made so that you can look at some distance from it. So that is recoil. So let's say the bullet is 20 grams. It's fired at 620 meters per second, so it's a rifle. It leaves the rifle at 12.4 kilograms meters per second. All right? What about the rifle? If the rifle is 5 kilograms, what is the speed of recoil going to be? Well, we take that momentum, equal and opposite, divided by the mass. It's going to kick back at you at about 6 miles per hour. That's why when people target shoot, they place the shoulder rest right up to their shoulder, so when it kicks back, okay, it's not just the rifle that's being pushed backward, it's you too. Okay? Just discharging this rifle without holding it tight, it's going to come flying back. And that's recoil. Rocket propulsion operates pretty much in the same way. But this time, instead of firing a bullet, we are pushing hot gas downward to propel the rocket upward. We talked about this when we did Newton's third law. For every action, there's an equal and opposite reaction. Okay? Push the rocket propellant downward, that's your action. The reaction is that you go upward. Okay? Any type of propulsion, by the way, is this action, reaction, and transfer of momentum. Road on a car, train on a track, you're putting force on something and pushing it backward. Well, that's how the rocket's going to work. But instead of pushing on something solid like the ground, you're pushing on the air, okay, or you're pushing the hot gas. So the rocket is accelerated as a result of hot gas being pushed downward. And in many cases, if you analyze this in terms of physics, we call this a reverse inelastic collision. In an inelastic collision, 2 objects come together and stick together. In this case, 2 objects, the rocket plus the fuel, okay, start together and then push apart. So momentum is conserved, and the kinetic energy, again, we'll talk about energy more later on. I love the sound of dogs barking, don't you? So here's one way of looking at it. We have a rocket. Let's say this rocket is now in space and it's basically stationary, and we want to go forward. We take this hot gas, we accelerate it backward, and that's going to push the rocket forward. This negative momentum of this hot gas pushes the rocket this way. Now, why do rockets have to have such a hot exhaust? I actually used to do a little program over the summer with middle school students as a part of NASA, and we used water rockets. We'd actually take soda bottles, fill them up with water and pressurized air, and the rocket would go upward. Well, the water, being, fairly low pressure, would not have very much momentum when it squirted out the bottom. Therefore, it couldn't transfer very much momentum to the rocket. In real rockets, which use hot gases, we have a very vigorous chemical reaction, which is going to cause the gas, remember the ideal gas law, PV equals nRT? If you want a lot of pressure, have a lot of temperature, we can get more momentum, have the rocket thrust come out at a higher velocity. That'll put more momentum into the rocket for the amount of fuel that you have to burn. So it's rocket science, folks. Okay? You understand rocket science now. Before liftoff, the rocket has no momentum. The fuel is inside the rocket. At liftoff, the fuel is combusted to create hot gas with an oxidizer, and this generates the upward momentum from the downward momentum of the hot gas. And again, we can see this with the space shuttle. The solid rockets are the part of the space shuttle that gave it the most amount of impulse. The hot solid fuel, as it combusted, became very, very high velocity gas, was pushed downward, and that created the upward impulse for the shuttle. Now, if you really want to go into in-depth rocket science, look up delta V. Delta V is the amount of velocity. It's sort of an abstract concept. I don't want to call it the amount of velocity, but it's what's needed to get to a particular orbit. We'll see that the delta V for most rockets to get up into orbit, just even in low Earth orbit, is about 10,000 meters per second. Okay, we come to that calculation because if we look at a rocket, and this is just a little model, actually this is a big model rocket, but this is a model rocket going upward, we can think of the mass of the rocket as being m and the mass of the hot gas being delta m. Okay? We want to increase our velocity from whatever it is to this new velocity by giving off more and more delta m, but doing it at a higher velocity. Now, I'm not going to get into the equation because, quite frankly, the equation actually goes into a fairly high level of math we call differential equations. But again, Newton's second law says force is equal to mass times acceleration. The acceleration of the rocket goes by how much delta V we have over how much time that's given off. Another way of looking at this is that the velocity of the exhaust, okay, is very much related to this concept of delta V. All right? See delta V on this side of the equation, we see delta V on this side of the equation. If you solve for all the right equations, all right, I'm going to hand wave right here because, again, I'm not doing differential equations for this course. But if we solve for all the different equations, regardless of the mass of the rocket, the amount of delta V that we can achieve, okay, how high in the orbit can we go, we'll see this in a second, is related to the velocity of the exhaust gas. The faster we can make the exhaust gas, the more delta V we can get for the least amount of fuel that's being spent. Most of the fuel of a rocket, about 80 to 95% of the mass of the rocket, most of the mass of a rocket is fuel and oxidizer. So we can make this a large number by simply making the rocket very, very large. All right? But we can make the rocket more efficient by making the exhaust more efficient. Solid rockets are good for giving you initial boost. But the reason why we don't use solid rockets necessarily to put payloads into orbit is because their exhaust velocity is kind of low. You need very big solid rockets to get even a small payload in orbit. Bipropellant liquid rockets, like the space shuttle was liquid hydrogen and liquid oxygen on its main engines. Falcon 9 is kerosene and liquid oxygen. The Delta IV Heavy is hydrogen and oxygen. But two things, fuel and an oxidizer are combined. There you can get a much higher exhaust velocity, so you need much, much less fuel. Okay? Now, the ultimate holy grail of rocketry is something called an ion engine. Unfortunately, we can't use ion engines in the atmosphere near the ground. So to get something up into orbit, the only way we know how to do it is to use a typical rocket with oxidizer. But once in orbit, we can use an ion engine to boost ourselves even further, maybe to the moon, maybe to Mars, wherever we want to travel. Now again, delta V has to be really, really large. 9.3 to 10 kilometers per second, okay, that's 9,300 meters per second to 10,000 meters per second is needed just to achieve Earth orbit. Doesn't mean you're necessarily, changing your velocity by that much, but if you do the calculation of the fuel that you need given a certain exhaust velocity, that delta V will get you there. 1.2 to 2.1 kilometers per second are needed to go from low Earth orbit to geostationary orbit. That's boosting a satellite into an orbit where it goes around the Earth every 24 hours. And if you want to escape Earth's gravity, you need about 3.22 kilometers per second, and that would be on like a trip to Mars. So you see, most of the energy, most of the momentum is actually gained just getting above the Earth's atmosphere. And again, this is the crazy formula that is used to find how much mass you need. This tells you how much mass you need compared to the mass of the rocket initially. And, calculations just to reach orbit, 90% of the rocket's mass has to be used even for the most efficient liquid oxygen, liquid hydrogen rocket. And again, an additional 50% of the 10% that's left over has to be used in an additional stage. And again, here's sort of different places if you really want to get into this. Going to different places, low Earth orbit, geostationary orbit, going to the moon, what all the delta V's in kilometers per second are needed. Going from one point to another. Again, this is more than we necessarily want to do in this level of course, but astronomy, rocketry, that always interests me, so I'm presenting this as sort of something that you can look into if you're more interested. And again, 9,400 to 10,000 meters per second just to get into low Earth orbit. And then you see anywhere you want to go in the solar system, there's a cost in delta V. There's a cost in how much fuel. So for instance, let's say we want to go to Mars. To get the rocket into orbit, first of all, we've got to use up fuel at around 10,000 meters per second. Once you're there, to leave Earth orbit, you have to add another 3,000. Okay? Now on the way to Mars, we need another 1,000 to get there. Okay? Another 1,400 to drop into a lower orbit. And then once you're in the lower orbit, you've got to then decelerate and hit the surface. So the reason why we haven't gone to Mars is it would be an incredibly large rocket to do so. Okay? With the current technology we have, it was difficult enough to go to the moon. Calculate the delta V for going to Mars, and you'll see that the size of the rocket actually grows exponentially. All right. Once again, turbofan engines are actually very efficient when we think of them in terms of rockets because the momentum that they generate is from taking air in and pushing it out the other side. They basically take mass from the outside and push it behind them. So therefore, when we're looking at efficiency, jet engines are so much more efficient than rocket engines. However, once you get above the atmosphere, there's no oxygen. There's nothing to grab onto and push off of. So pretty much the rocket's got to carry everything. All right? Now, we'll skip some of this. Here's a Delta IV engine. This is a very efficient engine, but actually very expensive. Even though it's more efficient than the Falcon 9 rockets that SpaceX uses, its greater cost is having the United Launch Alliance retire it. But again, the Delta IV Heavy has actually 3 Delta IV rockets together. And these are just big liquid oxygen, liquid hydrogen tanks. Eventually, we can make travel to other planets a lot easier. It's always going to be hard to go up into orbit. It's going to take a certain delta V, about 10,000 meters per second, just to get above the Earth's atmosphere. Okay? Are there other technologies that we could use instead of chemical? Well, they've actually tried to use nuclear rockets, and let's just say the amount of radiation that they produce is untenable for use. You know, basically, you'd be polluting the Earth's atmosphere with radioactivity using that. So chemical rockets are what we have right now to get up into orbit. But again, once up in orbit, ion engines make sense. Think about it. Instead of carrying fuel and oxidizer with you, you just carry some propellant, a mass. We then use electricity from solar panels to accelerate this mass. Now with a chemical rocket, the best you can hope for is about 4,400 meters per second. With an ion engine, you can accelerate these ions as fast as you want. So you can get a lot of delta V for very little energy. Here are different types of ion engines that have been worked on. This is one that was worked on by ESA. Eventually, this Vasimir engine is supposed to be the most powerful of the types of ion engines that we can use. It may be able to generate enough thrust to eventually be used on human rockets. But right now, these Hall effect thrusters, which are actually used on the Starlink satellites that SpaceX are putting up, are the most efficient way to produce propellant. Okay, so that's rocket science, a little bit of rocket science for you.